Okay, so today what I want to do is I want to work on multiplying these complex numbers. And I think it makes sense to see the multiplication being done in rectangular form, so essentially using FOIL, and then using the multiplication, or doing the multiplication using the polar or trigonometric form that we talked about yesterday. The polar form, if we go far enough in regards to the things that we want to multiply, if we multiply 6, 7, 8 different complex numbers together, polar form is undoubtedly the quickest, most efficient technique. Okay? If we're multiplying two numbers together, maybe foiling and working with the rectangular form is the most efficient. Does that make sense? A lot of times when you have shortcuts that provide efficiency, obviously there are situations, we've seen this with factoring and things like that, we've seen it in college algebra with some other things, the time consumption on kind of a small scale situation might be negligible, okay? And the shortcut that we have developed might not even be the shorter path when we're on a small scale kind of situation where I'm only multiplying two things together or three things together, okay? But on a large scale, the shortcut will undoubtedly be quicker, okay? So what we see today, we're going to go through some examples today, and you might not recognize the efficiency, okay? It might actually take us longer with the polar stuff, okay? But what happens is that a lot of this mathematics, this algebra, is involved in technology and computer programs that, for some need, will be multiplying complex numbers. So what they would do is take those complex numbers, they'll write a short program that takes that complex number that's in rectangular form, and it will convert it into polar, and it will do all the algebra necessary in polar to generate a product or a quotient or something like that, and then it'll have a short program that changes it back into rectangular. Does that make sense? So then that the program can actually use that rectangular coordinate. And maybe that's because maybe we're programming a robot to move or something like that, and it makes more sense to get that stuff completed and done in an efficient manner. So we wanted to change it to polar. The reason we do that, obviously, is multiplying very large complex numbers and a large amount of factors can bog down a computer. Does that make sense? Yeah, a lot of the accessible memory can be used, and your program's going to be slow, your machine's going to be slow, where if we can eliminate that, obviously create a more efficient computer, a more efficient program, and ultimately that turns into more money for the software companies. Does that make sense? Okay. So when we finished class yesterday, we were talking about this idea here that when we take z sub 1 times z sub 2, and they're in polar form, so let's say z1, trouble right here, z1 is equal to r1 cis theta 1, and z2 was r2 cis theta 2, then when I multiply those together and I look at what z1, z2's product is, it is r1, r2 cis, and we said it turns into theta 1 plus theta 2 as the argument. Okay? That's what we talked about yesterday at the conclusion of class. Okay? And we did one or two examples. Okay? I want to kind of extend this a little bit. If I have, let's just say, z1, z2, z3, all the way to z sub n, okay, what that's going, if I won't find that product, what that will end up looking like is r1 times r2 times R3 times all the R's that you have for all your complex numbers within this range. Does that make sense? Within this product. And then you'll have cis, and you'll go theta 1 plus theta 2 plus theta 3 plus all the thetas that exist inside that number of factors that you have. So if I have 10 Z1, Z2, Z3, Z4s, then I have 10 thetas that I'm adding together, right? I have 10 radii that I'm multiplying together, okay? And that kind of situation there is where polar form becomes an efficient procedure, okay? I want to do the same one we did with the last class. Actually, yeah, we'll do the same one we did with the last class. I want to take Z1 and I want it to be 1 plus I. I want Z2 to be 2 plus 2I. And I want Z3 to be negative 1 minus I. And I want to find their product, Z1, Z2, Z3. And I first want to do this in rectangular form. Okay, so I'll have 1 plus I, 2 plus 2I, negative 1 minus I. Nothing in those factors kind of work well together. What I'd be looking for in maybe choosing or using the commutative property to rearrange some products here is to see if there's anything that are conjugates, because that would simplify my product or my first foiling process. But there are no conjugates here. But there tends to be, as we multiply this out, something that's pretty convenient that happens that does not always happen. But it's the nature of, if I look at these, they're all, the A's and B's are the same in each one of these, right? So that A is the same as that B, that A is the same as that B, that A is the same as that B. So what happens is some convenient cancellations eventually, but that does not always happen. So if I'm going to multiply these out in rectangular form, I'm going to FOIL these two. So 1 times 2 is 2. 1 times 2i is 2i. I times 2 is 2i. And now because these coefficients are the same, A and B, now we have I times 2I, which gives me a plus 2I squared. And here's where the cancellation occurs. That I squared turns into what? Negative 1. And that negative 2 now and this positive 2 do what to one another? Cancel each other out. So that cancellation occurs because the A, the B, the A, the B, the A, and the B, they were the same. Okay? Generally speaking, they're usually not the same, or more often than not, they're not the same. So that cancellation might not always happen. But that gives me 4i when I multiply those first two together, right? Now what I need to do is still multiply by that last factor. And now when I multiply that through, I get negative 4i minus 4i squared. What's that I squared turn into? Negative 1, so it's going to change that to a positive, right? And now I was going to rewrite this in A plus BI form, so it gives me Z1, Z2, Z3's product to be 4 minus 4i. Is that okay? All right. Now there were some things, like I said, there were some things, cancellation there that made that a little bit quicker for us than it normally would. For most of the products that we get, we would, that 4i that we got down there when I started writing in blue would actually usually be a binomial, and I would have to FOIL again. Okay. Now what I want to do is I want to take and do the exact same process, but do it in polar form. So using really this blue formula here. Okay. So let's see if I can move some stuff up here. I don't want to delete this. All right, so that ended up giving me that there, right? Okay. So now I want to go through, I just trying to show you the comparison of the two processes. What I need to do, though, before I can use this second process here is turn each one of these into polar form. Now, it should not be all that difficult with these, because remember, if I'm trying to find R, that is your real component squared plus your imaginary component squared, add them together, divide, or take square root, right? That's the Pythagorean theorem there. Theta is going to be found by taking a tangent inverse of B over A. Okay, so we should be able to do that pretty quickly with these Z1, Z2s, and Z3s. 1 squared plus 1 squared would be 2, right? And put that under the square root. So my R for this first one is radical 2. Cis. Now when I do theta, it's tangent inverse of B divided by A. It's tangent inverse of 1 divided by 1 in this case. What's the tangent inverse of 1? 45 degrees, right? Okay, that's the only place on the unit circle where I'm going to get a positive 1 divided by a positive 1. Okay, as a quotient of the sine and cosine. All right, so that's Z1. Z2, I would take 2 squared plus 2 squared, so that's A squared plus B squared. It gives me radical 8. I'm going to write it that way. And then I go cis. Now, if I do tangent inverse of B divided by A, it'd be tangent inverse of 2 divided by 2, right? Is that tangent inverse of 1 again? Is that 45 degrees again? And then Z sub 3, negative 1 squared is 1, negative 1 squared is 1, add those together, get 2 underneath the square root. And then I go cis. Now here's where it gets tricky on this one. It's a little bit different. What quadrant is negative 1 minus I in? Third quadrant, right? Go left 1, down 1. Okay? So when we go tangent inverse, so left 1, down 1, we're looking at that point right there, right? When we go tangent inverse is going to give us that angle right there to be how big? If I go B over A, B is negative 1, A is negative 1, right? Tangent inverse of 1 then, right? It's going to give me that to be 45 degrees. But this is the angle we're interested in. How big is that angle? 180 plus 45, so 225 would be the theta there for that one. Is that right? Okay. So the idea, guys, is, doing it by hand, that took more time. We were probably already done with the rectangular foiling process once we got these things that we would time ourselves. Does that make sense? But if this was working inside a computer program or something like that, we would have code that would transform those very quickly. Okay, I can do it endless amount of times as fast as we needed to. Okay, so that shouldn't be hopefully that should not be a tedious task there in converting those into polar. So now when I want to go Z1, Z2, Z3, we're going to use this idea here. We take radius 1 times radius 2 times radius 3, and then cis theta 1 plus theta 2 plus theta 3. Now multiplying that stuff out, radical 2 times radical 2 is 2, right? Times that 2 would be 4. times my radical 2. So that stuff right there turns into 4 radical 2. Then you have cis, 45 plus 45 plus 225, 315. Okay. That right there is the product of Z1, Z2, and Z3 in polar form. Okay? Let's convert that into rectangular form then. Okay? Because usually that's kind of what we're interested in being able to do. We're provided Z1, Z2, Z3 in rectangular form to begin with. We convert it over to polar to do the math. And when we're done, we convert it back to rectangular to present our answer in the same format that the problem was provided. That kind of make sense? Okay. So now when I convert back from polar to rectangular, it's really easy. We just have to realize that the cis means cosine 315 plus I times sine of 315. And then we evaluate. What's the cosine of 315? Radical 2 over 2. What's the sine of 315? Negative radical 2 over 2. Okay, so now we distribute. 4 radical 2 times radical 2 is going to give me 8, right? And then I have 8 divided by 2. It's going to give me 4. And then when I take 4 radical 2 times this radical 2 over 2 again, it's going to be 4, but it's now negative. And then I multiply it by my I. We recognize those two things are the same, right? Okay. Now, I would agree that most of you are going to say, well, that was a much longer process than foiling. And it's much longer because we had to change them into polar, right? Okay. But what will end up being quicker is later on when I ask you to take 1 plus I or 2 plus 2I or negative 1 minus I and raise that to the 35th power. You don't want to FOIL that. Okay. But raising it to the 35th power using polar form is going to be pretty simple, pretty easy. Think.
Is the angle measurement add up to more than 360? What do you want us to use the terminal angle or just keep that?
Okay, so if we have an angle that ends up being, let's say, 405 degrees, okay, as our theta 1 plus theta 2 plus theta 3 or whatever comes up to be 405. You can use 405, but the best thing to do is find a terminal angle that is between 0 and 360. So subtract 360 from that, and you're going to get 45, right? And then, so that's the theta you're going to want to use because that's going to reference you to the unit circle. So that's a very good question. Last class we did one. We just chose some arbitrary values for A and B with Z1, Z2, and Z3. So let's kind of do the same thing here. If I go to Z1, let's say it's 2 plus 3I. Let's go to Z2 is 4 minus 5I. And Z3, let's go negative 6. That first quadrant, this would be fourth quadrant. It's for negative 6 plus I. And let's find that product. Z1, Z2, Z3. A lot of your homework questions are just asking you, I think, for the most part, to multiply just 2 of these together. If we can do it with 3, then you're going to be awesome at 2. If you do it with 3, it's just a little bit longer to do with 4. So the steps are very, very similar, no matter how many factors you have here. So I'm going to multiply those out. So what? 2 times 4 would give me 8. 2 times negative 5 will give me negative 10i. I'm going to get, what, 12i, and then negative 15i squared. And this is, more often than not, what happens, is that you get 8 plus 15, so it gives me, what, 23, plus then 2i, right? So in the last example, we were left with just the b part, right? The bi part, I think it was 4i. Here we're actually left with a new a plus bi, okay? This is what usually happens. The situations that you're left with just the a part or just the b part is when your coefficients for a and b in z1, z2, and z3, when they're the same, meaning that I've got 1 plus 1i, 2 plus 2i, negative 3 minus 3i, something like that, okay, for your z1, z2, and z3s. So that's 23 plus 2i is that product of these first two. We now need to FOIL that with negative 6 plus I, right? Okay. So 23 times 6, so that's 8. Carry the 1, 138. 23 times I then is 23i. 2i times negative 6 and negative 12i. And then 2i times I is 2i squared. The I squareds is negative, so now I have, what, 136? Oh, sorry. Yes. So this is going to be negative 140. Good call. So negative 140. And then plus 11i. So that's the product of Z1, Z2, and Z3. I don't know if you guys are aware of this, if you ever use this, your calculator will do, your TI calculator will do products of complex numbers. So just double checking before we go on. Negative 140 plus 11i. Okay. Okay. Let's now see if we generate the same exact solution. There's times where these things don't want to, there we go. So that was the solution, right? Negative 40 plus 11i. Now, let's do the exact same thing, but do it in polar form. So I'm doing it in polar form. I need to change those all to polar coordinates. Now, what's going to stink about this is when I find Z1, the radius part is easy. Remember, the radius is a squared plus b squared underneath the square root. Okay? If I go 2 squared, so 4, plus 3 squared, 9, I get root 13, right? And it'll be cis. Now, finding theta for that's kind of a pain in the butt. Finding theta for that, you're going to need to take your calculator, and it's, you're going to go to second tangent of b divided by a. B is 3, a is 2. Make sure in the right mode that you're interested in using. I'm going to use degrees. Okay, so it gets 56.3099. It's ugly because it's not a 60 or a 30 or a 90 or a 45, right? And this happens a lot. The one thing to pay attention to here, guys, is whether this is the direct angle that you use. This angle here, 2 plus 3i, or that point is in what quadrant? First quadrant, right? So this is the value that I need to use for theta. So it's 56.30993247. Now, the more decimal places you use, the more accurate this is going to check out in a little bit. The next thing I want to do is find Z2. So 4 squared, 16, right? 5 squared, 25. 16 plus 25, 41. Okay. And then we're going to write cis. And I'm going to go second tangent. I'm going to do B over A of 5 divided by 4. I never really care about the plus or minus of this, because I know that 51 degrees isn't the degree that I'm interested in anyways.
64 degrees right now.
Yes, it is. 51.34 degrees is ultimately kind of a reference angle. Okay? What quadrant is 4 minus 5i in? The fourth quadrant, right? Okay? So what I end up needing to do to find the theta here, kind of visualize this, and maybe a quick sketch isn't a bad idea, but that point right there would be your 4 minus 5i. This angle here is the 51 degrees. How do I find that angle right there? Good. And we get 308. .6598083. Then we do the exact same thing for Z3. So Z3, 1 squared plus 36. So 37 is my R. Cis. Now theta is going to be tangent inverse of B over A. Okay. 9.4 degrees. Now think about this. What quadrant should that be in? Second quadrant. So the 9 degrees is that angle right there, right? How do I find that angle? 180 minus it. So you get 170.53767778. Okay. Now, if I wanted to take and figure out what Z1, Z2, Z3 is, it's going to be the radii of each one of those multiplied together. So radical 13 times radical 41 times radical 37. Okay. And are those all prime numbers? So that's kind of a nice thing, I believe. And we go cis then. We're going to add all those angles up. So we had the 56. This is a nice thing about maybe using this calculator for this. I can go back up and just pick off those. I'm going to cut and paste them. Get this angle of 535.5074186. Okay, so when we take the 13 times 41 times 37, gives me 19,721. Then. Now you can use 530 because you're going to use your calculator here in a moment anyways. You can use the 535 number, or like Fanny said, remove that 360 from there, and 175 will give you the same information. 175.5074186. That is the polar form of negative 140 plus 11i. And now what I want to do is check to make sure that makes sense. So what we're going to do is we're going to grab a calculator. It doesn't matter what one you take. Okay. Let's use Desmos. I like I like decimals because I could, type it in and see it. That's the way I meant to type it in. Now it doesn't have a cis function, so I just got to type in cosine of the 175.507 4186, and that is obviously that's your A component, right? Because that's what we define A as. It's R cosine theta. So negative 140. And now, why is the 15 there? Rounding error, right? Okay. If I change this to sine, it gives me the 10.99999. What's that pretty close to? 11, right? And the only reason that it's different is because of the rounding error. That kind of makes sense? Okay, so this is kind of what we would have if we were writing a computer program. A computer program would be written to say, okay, have a tool that takes that to that, takes that to that, takes that to that, and then it does this math. And then it takes this here back up to that answer right there, and it displays or uses in that negative 140 plus 11i. Okay? Kind of a tedious process, right? Okay? But if we were to go 4 factors, 5 factors, 12 factors, the polar process is much quicker. Okay? Let's kind of do this. Let's talk about, what if I asked you to take, let's say Z1. I hate when that thing does that. I don't know why it does. I can't get rid of that now. Once I close the program, I'll just do the work in this one. Let's say Z1 is equal to, let's just say Z, it says Z1. This Z is R cis theta. And I ask you to take Z times Z. What we talked about yesterday would be that would be the radius of Z, or the radius of your first factor, times the radius of your second factor, right? And then it'd be cis, and then the theta of your first factor, your first complex number, plus then the theta of your second complex number, right? And you can rewrite that then as R squared cis of 2 theta, correct? What if I ask you to do Z times Z times Z? What's that going to look like? Yeah. Be R times R times R, cis of theta plus theta plus theta. So you guys made the jump right away to R cubed cis 3 theta. Okay? This is called a proof by induction, meaning that when I get to Z times Z times Z, all the way out to Z sub n, okay, or n times, that would be R times R times R n times, right? Okay? Well, how can I eventually rewrite that then? R to the nth, right? And it would be cis n times theta. And that is what Z to the nth is going to look like. Okay? Why is that a benefit to? So that theorem, this is a theorem here, is called I think it's an RE. Yep. It's called de Moivre's theorem. Okay? What it allows us to do is take a complex number, let's say, let's just say Z is equal to 1 plus I root 3. Takes that complex number, and let's say I want you to take that complex number. I want to find z to the 10th power. Well, you would have to do, now, if I was doing this in rectangular, there are some techniques here that I think we can use in rectangular form that might expedite the multiplication. Is that the same thing? Is that z to the 10th? Okay, so if I wanted to, then I could say, well, 1 plus radical 3i squared, well, that's 1. Square the first term. Multiply these two things together and double, so it'll be 2 root 3i, right? And then last times last would be 3i squared, so minus 3. So I would get, what, negative 2 plus 2 root 3i raised to the 5th power. Is that right? And what I would have to do then is recognize, well, then that means that is negative 2 plus 2 root 3i squared multiplied by negative 2 plus 2 root 3i. And I have to FOIL all that stuff out, right? Now, writing these as, the 5th power as something squared, times then that something is a convenient way of eliminating some of the FOILing. Does that make sense? I've had people in the past, if I asked them to do this, like to the 10th power, is that they would write this thing out, 1 plus I radical 3 10 times. So 1 plus I radical 3, 1 plus I radical 3, 1 plus I radical 3. I'm going to write it out 4 times. What they would do is they would FOIL those two, get a product, and then just pull this one down and multiply. Is that kind of stupid? Yeah, the idea is that once you get those two as a product, those two are the same product, right? So now it makes more sense because I know what this one already is, that this product is the same thing, and now I just FOIL those two new things, right? Still a pain in the butt. Let's see how this would work if we were using de Moivre's theorem. De Moivre's theorem says convert this thing into polar form. So in polar form, z is going to be, we take that and square it, right? We get 1. Take that and square it, so we get 3. Add those together and put it underneath radical, so it gives you 2, right? So we get 2 cis, okay? Now, theta here, theta is going to be tangent inverse of b over a, right? That's 60 degrees, isn't it? And it's in the first quadrant, so I know that 60 degrees is what I want. So theta is 60. Okay, so there's z. So now if I want z to the 10th, what de Moivre's theorem says is you take your r and you raise it to the 10th. And then you have cis, and you take 60, and you multiply it by 10. Okay? Now, sometimes, so here, 2 to the 10th is a large number. We should have our calculators, I think, can still do that. 2 to the 10th, 1024. Okay? If this was a much bigger number, and this as well, so it's like 2 to the 100th. We're going to run into problems with our calculator. We just write it as 2 to the 100th. But now, I get 600 in here, right? But what is a better number than 600 to use? 600 minus 360, which ends up being 240. Okay, so now this turns into 1024 cis, let's write it this way, cosine of 240 plus I sine of 240. What's the cosine of 240? So it's a 60-degree angle in this quadrant, right? So that's 60 degrees there. So the cosine, cosine is negative 1/2, isn't it? Okay. plus then I sine is going to be negative radical 3 over 2. So 1/2 of this is going to be, what, 512? It's negative 512. Plus then, be minus 512 radical 3 times I. Okay. So let's see. GeoGebra does a really good job of this. If we had, what would we say Z was? 1 plus square root of 3 times I. Oh, caps lock is on. Times I. And now if I ask this to take Z sub 1, raise it to the 10th power, my argument is that the coding in the background for GeoGebra is probably doing this, and it's probably taking that 1 plus radical 3I, and when I type this in up here in the input, it's taking and probably converting that into polar form so that I can do that math so much faster. Okay? Now, if I go 512 square root of 3, you see that is that number right there, right? Okay? So that's kind of the benefit of working with polar form, is that if I were to ask you to FOIL that out, you'd probably still be foiling, and we've got the answer. That kind of make sense? Okay. So that's the Moyer's theorem. What we're going to find out tomorrow is that there's an extension to the Moyer's theorem that allows us to take roots of complex numbers. Okay. And it has to do ultimately with a little bit of division. Go ahead and stop there. Couple assignments open, guys. You should be able to hopefully get at least that first one done by tomorrow. They're both closing off at 11:59 on their respective days. So one closes off tomorrow night, the other one closes off Thursday night. Keep working on those. You should before today's class should have been able to do all of the first one, I think. If you have questions, please don't hesitate to ask those.
Please pardon